All right, in our last video we talked about the Hall effect. Today we're going to talk about how a particle would, if passing into a B field, take on a circular path motion. All right, so imagine you have a B field, nice and uniform, and you have a charged particle in it, and your intention was to send it straight. Let's say you had a little gun and you fired a proton or an electron in, and would it take a straight path? That's the question. So if it is moving perpendicular to the field, so like the way I've drawn this, the field points into the board, the velocity points up the board. What would happen actually is there would be a force caused, and we have actually defined this force as proportional to Q and velocity and the B field and sine phi. So all of this can be experimentally confirmed that the force is proportional to the charge. It is also proportional to the velocity of the particle. It is also proportional to the B field. It is also proportional to the sine phi, where the phi is the angle between the B field and the velocity. So if this is my velocity vector and this happens to be sine 90, then we don't need it, right? So we kind of talked about that a couple days ago, and this is the magnitude of the force, and what is the direction? So we also had talked about the direction. The direction is according to the right-hand rule. So the right hand, has of course a thumb. You have your forefinger here like this, and then the other fingers like this. Sorry about the distraction there. Okay, so this is your palm. Okay, so basically, fingernails. I forgot fingernails. The right-hand rule dictates how the force will act. So you actually point your fingers and your forefinger in the direction of V. Your middle finger actually should point perpendicular to that. So if you can make a nice right angle there. I forgot to draw the middle finger sticking out at us is the idea. So this would be B. The force should be in the direction of your thumb. Okay. So sorry about the messy drawing, but we've done the right-hand rule. And if the particle is positively charged, it follows this right-hand rule. And then because there's a Q out front, and it is possible that Q is a negative quantity, say electrons flying, then you just kind of have to reverse the final force in the end. So you could just use your left hand for negative charge force direction, but we generally think right hand and then negate. Okay, so let's pretend that what's going in is actually a positive charge. So if you apply the right-hand rule and you point your forefinger up the page and your middle finger against the page, you will find that your thumb is pointing to the left. Okay, so this would be the force vector. Now what happens is the particle immediately reacts to the force and obeys it by accelerating into that direction. So now it would take on a path like this, you see, because it felt a perpendicular tug to the left. So I'll draw the tug in red. Okay, as soon as it deflects, though, its velocity vector has changed directions, as you can see. So it's now slightly up and to the left instead of straight up. And so I should draw my velocities in purple, sorry. Okay, so velocity was straight up, tug directly to the left. Now velocity is purple there, tilted slightly, and now it feels the force again, you see, perpendicular to it. And you can see that we've done this before in the mechanics sections of our book when talking about centripetal acceleration. So actually that is what's going to happen as long as the particle maintains its speed and doesn't change its magnitude. If it's the same speed the whole time, it should undergo uniform circular motion and basically cycle around in a circle. Okay? Now, all of this is very predictable because we know that according to Newton, the sum of the forces is always mass times acceleration, right? And for our purposes, the forces are in and out. So if this is the center, we have radially outward, which we can always call positive. And then we have radially inward, which we can always call negative. Okay, so assigning directions is a pretty simple thing. You would just say, look, it's got a force pulling it radially inward. So you would have a negative r hat for a direction. And a quantity of force is qvb sine phi. I forgot the v, qvb sine phi. Right? It's the only force in town, actually, so this is just equal to ma. Centripetal acceleration can be kinematically shown to just simply be v squared over r, right? And the acceleration is radially inward, so it too is negative r hat. So just from a magnitude standpoint alone, you basically can see that your radius of motion is always going to be mv squared over qvb sine phi. Now, if you further restrict the situation to make phi 90 degrees, then you don't need the sine phi. It's just 1, you see. Okay, but you can see that an object that's more massive would follow a larger radius. So if you had a proton and an electron, right, they have the same charge, and if you sent them in at the same velocity, the larger mass object, which is clearly the proton, would take on a larger radius circle. Oh, by the way, one of the v's cancels, right? So you can get rid of this v. Also, a particle traveling in at a higher velocity would, of course, make a larger circle. In fact, the top, if you look at it closely, is momentum, right? It's momentum. You might recognize mv from your kinematic studies, right? Or from your, I should say, your mechanics studies. And then down below you see q. What does that mean? Well, if the q is on the bottom, then the bigger the charge, the less radius. So let's say you sent in 2 equally massed particles at the same speed. Well, the one with more charge would actually make a smaller ring. Interesting. Then there's the B down here as well, which means if you really crank up the B field, your particles are going to spin around in smaller radius circles. So that's all very fun to think about. Now let's take a look at how long it takes for the particle to make one turn. Okay, so assuming that it doesn't accelerate angularly and it's actually going to maintain a constant angular velocity, we could just say that the time it takes to go around, so we call that one period, the time it takes to make one complete turn is simply 2 pi r, which is your distance, right? Meters divided by your velocity, which is meters per second. So this would just come out to seconds, obviously. So how many seconds? Well, let's plug in the r function that we just had. So you would just basically go t equals 2 pi r over mv over qb sine phi. In other words, 2 pi r, Mr. Shore messed up. I don't know why I plugged in the, I misread my own writing. Good grief. Mr. Shore is very sorry. The quantity right here is a v. I thought it was an r. I'm plugging in, let me highlight, all of this into here, excuse me, and I just dropped my quiz. Okay, that's okay. So anyway, back to the drawing board. Mr. Shore was going to do t equals 2 pi formula over v, and that formula is mv over qb sine phi. So this is kind of a fun formula too. If you notice, the v cancels out. You get 2 pi over qb sine phi, which basically means, if you look at it, that the only thing that can affect the period of motion, the circulating period of motion, the only thing that could affect it is the actual charge and the B field quantity. So the mass would not affect how long it takes to go around a circle, only the incoming charge. Also, the incoming velocity doesn't matter. Although maybe there's a really fast coming particle and it flies into the field, well, it's going to not matter if it flew in fast or slow. It's going to take the same amount of time to do a loop. It will travel a larger circle with its larger speed and therefore take the same amount of time to go around. So it's kind of a cool formula too, just to kind of look at. Remember, the sine phi we can easily treat as 1 if we further dictate that the phi is 90, right? So I always thought that was cool. And you might remember another quantity called frequency. And frequency is how many times it goes around each second. So it's cycles per second is the concept of frequency. And cycles per second would be basically the number of cycles per second is basically 1 over the number of seconds per cycle. So like there's another way to think of it algebraically, just move the cycle to the bottom of the bottom. In other words, 1 over period. So you could just basically flip your formula upside down here, this one here, and put QB sine phi over 2 pi. So QB sine phi over 2 pi, and you'll need one more thing, the mass, which I somehow copied wrong. Let me go back one more slide real quick. We were doing this formula, and I plugged this into the yellow, and there was an m, but for some reason I forgot to copy it. It's actually right here. 2 pi m over QB sine phi. And I'm just saying, if you flip that over, you get frequency. In fact, I'll just do it right here on this slide. So frequency, which is 1 over period, is just QB sine phi over 2 pi m. So mass, I should have been more cautious. I said something wrong a moment ago. I said the incoming mass doesn't matter. It does matter. The mass and the charge matter, not the velocity. So because I made a copier, I made a false statement. And if you think about my false statement, it didn't make sense anyway. So, okay, so looking at these equations, you could figure out how long it takes for the particle to go around once, or you could figure out how many times it goes around in 1 second. This is measured, of course, in seconds, and this is measured in what's called inverse seconds, also known as a hertz. Not as in the rental car, but, or, you know, I hurts my leg kind of thing, but hertz meaning inverse seconds. All right, frequency. So I thought those were things that we kind of already talked about. Now, one more thing about this. If the particle comes in and the phi is not 0, then something interesting will happen. So let's take a look at that. Let's say that you have your B field, and the particles come in, but they actually come in sort of pointing. So let me draw these B fields kind of as a, let's kind of draw them as tubes. So I know they're not tubes, but they're actually vector arrows. But let's say we kind of draw them like this. So you can kind of see them. So we're kind of looking at them from the back, but also sort of from the front, or from the side. And in fact, let me just kind of redraw entirely. Your B field is pointing like this. It's supposed to look like it's kind of away from you, so that the heads are further away from you. So if you can imagine that, maybe I can draw like a little table here to help you see that. Okay. So these are pointing. Let me lower them. They're not perpendicular to the desk. They're pointing kind of off at an angle. Okay, so if this is the case, and let's say you send in a particle flying this way, and it is constant distance above the desk, so this distance doesn't change above the desk. As it flies in, it's going to take a helical path, okay, sort of wrapping itself around the field line. And the reason is the B field line here, what it can and cannot do. The B field line can only influence the velocity and momentum of the particle in a dimension other than the dimension it points in. Okay, so for example, if this is in the direction, you know, b sub x, b sub y, b sub z, right? If that's your B field vector, and your velocity is coming in at, you know, velocity equals v sub x, v sub y, v sub z. The B field line can actually do no work. So that means it cannot change at all the speed of the particle. All it can do is change the direction of the particle. And so, and we can talk more about that later, but if let's say that the z component is the only non-zero component, so this is just an example. Let's say it's 0, 0, 10 Tesla, which is huge. Let's do 10 to the minus 3 Tesla. And the particle comes in with a velocity, 4 meters per second, 5 meters per second, 0. Okay? So I'm sure you could line it up this way. Then what happens is the Teslas can modify the 4 and the 5, but they can't modify the 0. So it's interesting how that works, but it comes from the nature of the cross product. So in other words, you know that 4 squared plus 5 squared is 41, right? So square root of 41 is actually the speed of the particle. The speed of the particle will always be square root of 41, but these values might change. Like there may be an instant when the speed vector, the velocity vector is, instead of 4 and 5, these numbers, might change to, let's say, root 40 and 1. But, if you square those and add those in the square root, you still get root 41, if you get my point. So what I'm trying to say is the z component of the velocity can't change because that's the direction the field's pointing in. That's kind of a fun fact there. And this is what we call a helix, this shape. So we call it a helical path, a helical path. And that can happen as long as the velocity has any component in the direction of the field. So since there was zero velocity, it would, and if it was zero, then it would just kind of cycle around like this in a circle. But if this was, say, v sub z, that value would never change. So I kind of said that wrong the first try. But it's always square root of 41 for these first two, and then that will never change. And if it is 0, you'll get a perfect circular motion. But if it's anything else, it'll move in a helix path. Okay? Okay, so then that brings up two ideas, V perp and V parallel. So V parallel in this context would be like the VZ, because that's parallel to the field. And then the V perp is more like, square root of Vx squared plus Vy squared. Vy squared. Okay, so sorry, I kind of foibled that a little bit by putting that 0 there. All I'm saying is that Vx and Vy can be affected by the field, but Vz cannot be, and therefore Vz is a constant, and V perp is a constant, but not Vx or Vy. Okay? So that's kind of an interesting thing. And then if you draw one more triangle here, if this is the B field line, and the particle is coming along like this, or let's say the particle is doing the helix thing, right, around, it's got two speeds. It's got V parallel, and it's got V perp. V perp is sort of its tangential velocity as it goes around. So if you see it from the front, V perp is perpendicular to the B field line. Let's say the B field line is pointing away from you. V parallel is, along the field line, okay, as shown here. Okay, so one thing we could do is draw like a little triangle like this. This is the total velocity, and it's made up of V perp and V parallel. Actually, let's switch them around. Let's put the V parallel as the x component, as the first component. So V parallel V perps, because it's got two dimensions to it, two things to it. So then basically phi would be that angle with the B field. So here's your B field pointing along the black. So let's write B in black. So basically, if you kind of do a little SOHCAHTOA, you can learn that V parallel is really just V cos phi, and V perpendicular is V sine phi. So what this does is this relates what we call the pitch angle, phi. It relates it to the original velocity. So if you take the original velocity times the cosine of the pitch angle, that gives you V parallel. If you do original velocity times sine of the pitch angle, you get V perpendicular. And these might be useful in the lab. So now I'd like you to go ahead and study magnetic mirrors. I'll send you that to study.